In some instances, we can also use division with the reverse tabular method to factor polynomials. So take this question. Is x plus 2 a factor of this polynomial right here? So to figure that out, we could either use the remainder theorem by plugging in -2 for x, but I'm actually going to find the quotient by setting up a reverse tabular here in order to see if there's a remainder and find the quotient. So remember, I'm going to draw 3 vertical lines here, and the way I find that out is noticing that I'm dividing a degree 4 by a degree 1. So when I divide those two, remember you subtract those exponents, so you should end up with a third degree polynomial. So there should be 1, 2, 3, 4 spots. Okay, so I'm going to set up my diagonals. The first one's 3x to the 4th. This diagonal right here should add up to 7x to the 3rd. This diagonal should add up to -25x squared. This diagonal should add up to -63x, and the last one should be the constant -18. So if x plus 2 is a factor, then I should get -18 in this box when I'm done. So I'm going to start up here, pop in 3x to the 4th, and notice that I would need to multiply x by 3x to the 3rd to get that 3x to the 4th in the box. So now that I have that, I'm going to take what I have on top, the 3x cubed, and multiply that by 2 to get 6x cubed in this bottom box. From there, I'm looking along this first diagonal and noticing that it needs to add to 7x cubed. So I would need an additional 1x cubed in that diagonal. And I work backwards from there. So if I had x squared up there, x squared times x would get me that, and 2 times x squared is 2x squared. This diagonal now needs to add to -25x squared, so I would need to have -27x squared in that box for those to sum to -25. So -27x is up there, and -27x times 2 is -54x. So I'm just working backwards here from my multiplication facts. Again, I notice that this diagonal needs to add to -63, so that means I would need -9 more x's to make that happen. Again, if there was a -9 up here, then -9 times x would get me -9x, and -9 times 2 is in fact -18. So these boxes match, so there is no remainder in this case. So if I'm answering, is x plus 2 a factor? Yes, x plus 2 is a factor. As a matter of fact, we can rewrite this polynomial as x plus 2 times your quotient, which we found up here. 3x to the 3rd plus x squared minus 27x minus 9. It's like if you were taking 20 and dividing it by 4. The quotient is 5 because 4 times 5 is equal to 20. So we're walking into that same issue here where this polynomial that we started with, the 3x to the 4th and so on, can be rewritten as x plus 2 because when I divide it, x plus 2, it goes in evenly, times 3x cubed plus x squared minus 27x minus 9 because that's the quotient that we get. So that's like the 5 in this case, and the x plus 2 is like the 4. So we have in fact factored that 4th degree polynomial, but there might be a little bit more we could do to factor here. So the x plus 2, that binomial in the front, there's nothing I could do there. But remember, every time we have 4 terms, if it is factorable, it's always going to be a factor by grouping problem because there are 4 terms. So let's take a look at this here. If I group those first 2 terms, it looks like I could just pull out an x squared from them to be left with 3x plus 1. And then if I group the next 2 terms, if I'm trying to pull out a greatest common factor, -27 and -9 both have a 9 in common, but I'm going to pull out a -9 to make sure that I get the plus sign in the parentheses so that I can group this correctly. So -27 divided by -9 is positive 3, and I've got the x, and -9 divided by 9 is positive 1. Okay, so this is working out so far. So I'm going to rewrite that binomial out in front because that x plus 2 just keeps chugging along. And I'm going to factor out that 3x plus 1 times my leftovers, the x squared and the minus 9. So as always, you want to factor until there's no more factoring that you can do. So this is almost factored completely here. So we used long division to get to this first step, and then we did some factor by grouping to get to the step we're at now. And as I'm scanning through my binomials, I notice that I don't have any greatest common factors, but x squared minus 9 is in fact a difference of two squares because x squared is a perfect square and 9 is a perfect square. So the last thing you can do to factor here is just separate that binomial into x plus 3 and x minus 3, and you have factored all the way.